GJ1214b is a sub-Neptune about 48 light-years away with a mass roughly 6.5 times Earth's and a radius 2.7 times larger. Early transmission spectroscopy revealed a nearly featureless spectrum when the planet passed in front of its star, meaning starlight wasn't being absorbed by specific molecules in predictable ways. This suggested either a high metallicity atmosphere, meaning an atmosphere with more heavy elements than hydrogen, or a thick layer of clouds or haze obscuring everything below. More recent infrared observations have detected the planet's own thermal emission, allowing astronomers to map how heat moves across its surface. The data points toward an atmosphere that is not hydrogen-dominated. Instead, it likely contains abundant heavier molecules, with strong evidence for water vapor, though distinguishing water from methane and other molecules remains challenging. The leading hypothesis is that GJ1214b is a water world, not in the sense of a planet with surface oceans like Earth, but a world where a significant fraction of its total mass is water or other volatiles. At the pressures and temperatures inside GJ1214b, water would not exist as a liquid ocean or water vapor. Instead, it would transition into exotic high-pressure ice phases deep in the interior, surrounded by layers of supercritical water closer to the surface. Supercritical water is a state where the distinction between liquid and gas breaks down. It behaves like a dense fluid with properties of both phases. Above this would be a thick steam atmosphere mixed with hydrogen, helium, and possibly methane or ammonia. The planet shows efficient day-night heat redistribution, meaning heat from the star-facing side is transported to the night side, likely through global atmospheric circulation. The thick haze or cloud deck makes direct observation of the lower atmosphere nearly impossible. GJ1214b is observationally stubborn, hiding its secrets behind layers of opacity and physically exotic, occupying a regime of pressure, temperature, and composition with no analog in our solar system. Coconuts 2b is a planet that exists at the edge of what we consider gravitationally bound. It orbits its small red dwarf star at roughly 7,500 astronomical units. To put that in perspective, Pluto orbits our sun at about 40 astronomical units. This planet is nearly 200 times farther from its star than Pluto is from ours. At that distance, a single year on Coconuts 2b takes over 1 million Earth years to complete. Human civilization has existed for less time than it takes this world to circle its star once. The planet itself is Jupiter-sized, with a mass roughly equal to that of our largest gas giant. But what makes it truly alien is its temperature and isolation. Coconuts 2b doesn't receive meaningful warmth from its distant star. Instead, it glows faintly in infrared at about 480 Kelvin, which is roughly 200 degrees Celsius. This heat comes from the leftover energy of its formation, energy that has been slowly radiating away for billions of years since the planet coalesced from gas and dust. Scientists classify it as a T9.5 spectral type, right at the boundary between the coldest brown dwarfs and true planets. Spectroscopic analysis reveals something even stranger. The chemistry in its atmosphere is out of balance. Molecules like carbon monoxide and ammonia exist in ratios that don't match those predicted by simple thermal models. This disequilibrium chemistry suggests complex atmospheric processes, possibly vertical mixing or photochemistry driven by cosmic rays rather than starlight. Cloud signatures appear in the data, along with unexpected flux patterns that indicate we don't fully understand how clouds form and behave at these frigid temperatures. Coconuts 2b was originally mistaken for a rogue planet drifting through interstellar space. It's that disconnected from its star that's solitary in the cosmic dark. Rogue planets are worlds that have been ejected from their star systems, either during the chaotic early phases of planetary formation or through gravitational interactions with other planets or passing stars. Microlensing surveys and recent direct detections suggest the Milky Way may contain billions of these objects, possibly outnumbering stars themselves. Without a star to warm them, rogue planets are frozen and dark, drifting through interstellar space with surface temperatures approaching the cosmic microwave background, about 3 Kelvin or minus 270 degrees Celsius. But beneath their frozen surfaces, some rogue planets could remain geologically active for billions of years. Radioactive decay of elements like uranium, thorium, and potassium generates heat in a planet's interior. For a large planet with a thick ice shell, this internal heat could maintain a subsurface ocean of liquid water, similar to what we believe exists beneath the ice of Jupiter's moon Europa or Saturn's moon Enceladus. These oceans would be completely isolated from sunlight, warmed only by geothermal heat from the planet's core. Tidal heating is another potential energy source if the rogue planet has large moons. Gravitational interactions between the planet and its moons could generate tidal flexing, creating friction and heat in both bodies. This could sustain liquid water or even drive hydrothermal activity on the sea floor. The possibility of life in these environments is speculative but scientifically plausible. On Earth, life exists in deep-sea hydrothermal vents, ecosystems that derive energy entirely from chemical reactions rather than sunlight. A rogue planet with a subsurface ocean and active geology could, in theory, support similar ecosystems. These worlds would be terrifyingly dark, devoid of stars or sunlight. Yet beneath their ice, they might harbor some of the strangest life in the galaxy, sustained by heat from within rather than light from above. TOI 849b orbits its sun-like star once every 18 hours. This ultra-short period places it deep within what astronomers call the Neptunian desert, a region close to stars where Neptune-mass planets are almost never found. The planet has a mass of about 40 Earth masses, similar to Neptune, but its radius is only 3.4 times Earth's. That makes it extraordinarily dense, with a mean density around 5.2 grams per cubic centimeter, comparable to Earth itself and far denser than any gas giant should be. The leading explanation is catastrophic. TOI 849b is likely the naked core of a gas giant that lost its hydrogen and helium envelope. Either extreme ultraviolet radiation from its star photoevaporated the atmosphere over millions of years, or gravitational interactions with another planet or the star itself tidally stripped the outer layers away. What remains is a world composed almost entirely of rock, iron, and possibly high-pressure water or ice phases, with only trace amounts of light gases clinging to the surface. The equilibrium temperature exceeds 1,500 degrees Celsius. At that heat, any remaining atmospheric components are being actively driven off into space. TOI 849b gives astronomers a rare direct look at what lies beneath the clouds of Jupiter and Saturn. Our gas giants hide their cores under tens of thousands of kilometers of hydrogen and helium. Here, the core is laid bare, a compressed ball of heavy elements heated to furnace temperatures by both stellar radiation and its own gravitational compression. The planet may have started as a massive gas giant, many times Jupiter's mass, or it could be a failed giant that grew a huge core but never accumulated the gas envelope it was meant to have. Either scenario rewrites our understanding of how giant planets form and die. 55 Cancri E completes an orbit in less than 18 hours, circling so close to its star that the day side is hot enough to melt rock into a global ocean of magma. Surface temperatures reach several thousand degrees Celsius. For years, scientists assumed the planet would be tidally locked with one molten hemisphere and one relatively cooler night side. But recent observations from the James Webb Space Telescope have revealed something far stranger. The planet's thermal emission varies dramatically over time. Its brightness pulses, suggesting the surface temperature and reflectivity change on timescales of hours to days. This isn't weather in the familiar sense, it's a feedback cycle driven by the magma ocean itself. When the surface heats up, silicate vapor escapes from the molten rock, rising into the thin atmosphere. This vapor can condense into reflective clouds at higher altitudes. Those clouds then block incoming starlight, cooling the surface and reducing the rate of evaporation. With less vapor, the clouds dissipate, the surface heats again, and the cycle repeats. Spectroscopic data between 4 and 12 micrometers rule out a purely rock vapor atmosphere. Instead, the planet appears to have a substantial volatile layer, probably rich in carbon monoxide or carbon dioxide sustained by continuous outgassing from the magma below. This creates a bizarre atmosphere where gases are constantly being recycled between the molten surface and the sky above. Lava worlds represent a broader class of rocky planets where entire hemispheres become molten seas. Gases escape from the magma through outgassing, primarily silicon monoxide, silicon dioxide, and metal vapors. These gases are blown by winds toward the cooler night side, where temperatures drop low enough for silicon dioxide to condense into solid particles of quartz. These particles form clouds that drift in the upper atmosphere before precipitating as sand rain or sand snow. The sand grains fall back to the surface, where they may be transported by surface flows back toward the day side, melting again and releasing gases to restart the cycle. The night side could have a thin crust of solidified rock, constantly fractured and renewed by thermal stress and by fresh magma bleeding through from the day side. HD 189733b is a hot Jupiter located about 64 light-years from Earth. Its day side reaches temperatures around 900 to 1000 degrees Celsius, but the planet's most notorious feature isn't the heat, it's the weather. Wind speeds on HD 189733b are estimated at roughly 8,000 kilometers per hour, which translates to about 5,000 miles per hour. That's nearly 10 times faster than the most powerful hurricanes on Earth, and fast enough to transport atmospheric material almost at supersonic speeds. The planet is tidally locked, so one hemisphere always faces the star while the other is in permanent night. This creates an extreme temperature gradient that drives the winds. Heat from the day side flows toward the cooler night side, creating a massive equatorial jet stream that circles the planet. Spectroscopic observations reveal silicate particles suspended in the upper atmosphere. At the high temperatures on the day side, minerals like magnesium silicate and iron silicate vaporize. As winds carry this vapor toward the night side, temperatures drop and the vapor condenses into tiny solid grains. These grains fall as rain, but not straight down. The violent winds blow them sideways at hypersonic speeds, creating storms of razor-sharp glass particles moving faster than bullets. Recent spectral analysis has also detected hydrogen sulfide in the atmosphere, the same compound that gives rotten eggs their distinctive smell. If you could somehow survive the heat, the abrasive silicate storms, and the crushing atmospheric pressure, the air would reek of sulfur. Wasp 127b takes atmospheric extremes even further. This puffy hot Jupiter has an equatorial jet stream that reaches approximately 20,500 miles per hour, roughly 19 times faster than the fastest winds observed on Neptune. At these speeds, atmospheric dynamics enter a regime where compressibility effects, shock waves, and supersonic turbulence become important. The atmosphere isn't just flowing, it's behaving like a supersonic fluid, with potentially chaotic eddies and instabilities that we don't yet fully understand. The planet's low density suggests an extended atmosphere with a very gradual transition from gas to space, making it vulnerable to atmospheric stripping by stellar winds and radiation. Wasp 121b is a hot Jupiter so close to its star that tidal forces have stretched it into an elongated, football-like shape. The planet may be approaching the Roche limit, the distance at which tidal forces could begin to tear it apart. Dayside temperatures exceed 2,500 degrees Celsius, hot enough to vaporize most metals. Hubble Space Telescope observations have revealed that the upper atmosphere contains gaseous metals like iron, magnesium, chromium, and vanadium. On the day side, these metals exist as vapor, but as atmospheric circulation carries this vapor toward the cooler night side, temperatures drop and the metals condense into clouds. These aren't water clouds. They're clouds made of liquid metal droplets and possibly even solid metallic particles. As these clouds precipitate, they fall as liquid metal rain. Some models suggest that at certain temperatures and pressures, carbon compounds in the atmosphere could condense into solid particles of graphite or even microscopic diamonds, leading to the nickname gem rain. The condensed metals don't stay on the night side. Powerful winds driven by the temperature difference between hemispheres carry the droplets back toward the day side where they evaporate again and the cycle repeats. Wasp 76b operates on similar principles but with even more dramatic iron weather. Its dayside temperature reaches about 2,400 degrees Celsius, hot enough to vaporize iron and many rock-forming minerals. Strong winds blow iron vapor from the superheated dayside towards the permanent night side. As the vapor crosses into the cooler hemisphere, it condenses into liquid droplets and falls as molten iron rain. This creates a bizarre meteorology where liquid metal precipitates from the sky, only to be vaporized again when winds carry it back to the day side. The entire planet operates as a massive distillation system for heavy elements. Kelt 9b represents the absolute extreme of planetary temperatures. Its day side reaches approximately 4,600 Kelvin, hotter than many small red dwarf stars and only about 1,200 Kelvin cooler than the surface of our sun. At these temperatures, molecules cannot remain intact. Even molecular hydrogen breaks apart into individual atoms. The intense ultraviolet radiation from the host star is so powerful that it drives atmospheric escape at an extraordinary rate. The planet is surrounded by a glowing envelope of escaping hydrogen, creating a tail that streams away from the star like a comet. Kelt 9b may be losing more than 10,000 tons of atmosphere per second. The planet's atmosphere is also likely undergoing photodissociation, where ultraviolet light breaks chemical bonds faster than they can reform. This creates a chemically active, ionized upper atmosphere that behaves more like a stellar corona than a planetary atmosphere. The line between a hot Jupiter and a failed star becomes blurred at these extremes. Kelt 9b will not survive indefinitely. Over hundreds of millions of years, the combination of mass loss and potential orbital decay could reduce it to a smaller, denser remnant or cause it to spiral into its star entirely. Kepler 70b, if its existence is confirmed, pushes beyond even Kelt 9b into territory that defies planetary classification. It orbits an extremely hot subdwarf star at only 0.006 astronomical units with a surface temperature possibly near 6,900 degrees Celsius. At this temperature, rock doesn't just melt, it vaporizes completely, and even refractory metals like tungsten would exist as gas. This is a world where the distinction between solid, liquid, and gas becomes meaningless. It orbits in a realm where gravity barely holds it together against the fury of stellar radiation trying to tear it apart, atom by atom. The universe has created worlds stranger than most science fiction imagined. From water worlds shrouded in perpetual haze to planets where it rains molten iron and glass. From frozen wanderers drifting in eternal darkness to worlds so hot they blur the line between planet and star. These extreme exoplanets force us to expand our understanding of what's possible. We've discovered thousands of exoplanets, and the diversity is staggering. Every new discovery reminds us that our experience with 8 planets is a tiny sample of cosmic possibility. The weirdest planets challenge us because they operate in regimes that don't exist in our solar system, and we've barely begun to explore. If you found this journey through alien worlds fascinating, subscribe for more deep dives into the cosmos and check out this video next. Thanks for watching.